today we have our invited speaker, Adrián Pérez Salinas. He did his PhD on quantum algorithms with José Ignacio Latorre and Artur García. And now he's doing a postdoc in the Free University of Berlin. And today he's going to talk to us about, well, the title of the talk is Towards a Framework for Analyzing Quantum Machine Learning Algorithms. Whenever you want, Adrián, the floor is yours.
Thanks, Bea. So thanks for the invitation. Thanks anyone for being here. And it's a big pleasure to be in this piece. I was talking to Bea before. There is this conference happening in Madrid in not that much from now. Sign up because it's a very interesting thing. I was last year, and I think it's a great environment. So, as I was saying, I'm Adrián. I've been working my entire career in this field of quantum machine learning from many different perspectives, and I would like to present you a bit of how I see the field right now, what I think it's interesting, what I think should be done, and I really hope that you can learn anything from my perspective and from my point of view. I would like to say, please, at any point, interrupt me and let me know if you have any comments or any doubt or any question or any sort of feedback, because it's really very well appreciated. So I'm presenting here this some numerical framework for analyzing quantum machine learning algorithms in a compilation of works that I've made with Xavi on it, and who was a postdoc in Leiden with me when I was there, Hao Wang, a professor also there, and Berta Casas, who is now in the Barcelona Supercomputing Center. And this is intended to be a talk with some more or less broad perspective of how I see it. So we will be talking now about some introduction that will take most of the talk, because I think it's the motivation is the more relevant part of most of the talks, and then our 3 projects that we have that we have developed, and then to some conclusions. Introduction, I think it's the most important part. So if you have any question there, stop me. If we stop at the second section, it's perfectly fine. I think it's still the most important section of it. Bea, how long do we have? Sorry. I'm seeing that I'm not sharing.
No, you're not sharing now. Yeah.
Yes.
Normally it's like 45 minutes of talk, and we let some time for questions, but whatever. Like, it's more or less up to you.
Okay. My apologies. The incident really distracted me for a moment.
Don't worry.
Yes. Sorry. Again, so this is the title, the people that I'm working with, and a bit of the outline. Okay, fine. Sorry, guys. Then we are working in this framework of machine learning, right? So what is machine learning? Machine learning is this whole selection of techniques that allow to program a computer to solve a particular task without explicitly programming this computer to solve this explicit task. That means you don't really need to know how to solve that task. You just need to provide the computer with data that comes from somewhere, and the computer will be capable of learning the inner features of this data in such a way that it can infer what will be the solutions to previously unseen instances. From a more formal point of view, what we have is some data that are samples from some inaccessible distribution. And we developed some learning model, some algorithm A that yields some hypothesis function, h of x of I, where x is the data. Then we have a family of hypothesis functions, and depending on the data that we see, we can select this is right for our data, this is wrong for our data, and with this we can optimize and select which is the function that we would like to use. So how do we do that? In general, we have to train this model. And training this model means that this model can learn more or less what data is doing in the part of the data that we have seen. But this is not learning. This is just memorizing. You could know all the rivers in a country, and this still would never tell you how to read a map. So we need something else, which is called generalization, which is how this learning performs in data that you have never seen. So how is it to go into previously unseen data, right? So data is going to be the central element of all this game. And the main difficulty here is how to interpret this data. What are we doing to this data? Depending on how we treat this data, these results are going to be better or are going to be worse. And I'm going to give you a classical example of that. This is a classic problem from statistics that happened in the Second World War. So the task is the following. I am a member of the army. I don't remember which army actually, but it doesn't matter. And I would like to reduce the number of casualties in my planes, in my war fighters, whenever I send them into the battlefront. And so what I do is I go into the fighters that came back to the headquarters and look where are the bullets or where are the holes that were given by the bullets. And you see a distribution like that. So the question is, how should we reinforce the planes in such a way that the planes are as protected as they can be? And the first thing that one could think is, well, you have to stop. You have to put some shield, some protection in the areas that have been holed with bullets from the enemies. So that means more or less the center of planes and the tails and the extreme of the wings. Fine. But now someone smarter than I was appeared and say, listen, there are some parts of the plane that didn't get a bullet. That has to mean that whenever a plane gets hit in that area, it falls down. So where do you have to cover that? It's specifically in the areas that never received some impact. This is in statistics known as the survivor bias. But the message that I would like to deliver here is data is something that you cannot treat as raw, and you cannot expect it to give you the absolute solution without thinking about it. You need to really understand what is the role of the data so that machine learning works in a particular way. And this leads us to two different models in the learning framework. Right now, I'm the classical machine learning. So I'm in the world of classical computers and big data centers and so on. But there are mainly two different approaches, or two extreme approaches here. One of them is the supervector machines, or supervector classifiers, or supervector. Always the supervector are in the names. So these are algorithms that are capable to optimally and linearly separate data. And as you have some data, and the task is to draw a line that separates data as good as it can be. This is always possible. This is always efficient, and this is always optimal. So everything is fine. The main limitation here is that the supervector machine can only perform linear classification. So that means that if your data comes from God knows where, and it's not linear, these kernel tricks are never going to work. Sorry, these supervector machines are never going to work. To extend the applicability of the supervector machines, we have something called the kernel trick. So what does it mean, the kernel trick? Formally speaking, and for those that are invested in maths, this means that the data can be embedded into some space of inner product that is that works only in the gram matrices of the data. But the important part is that with this kernel, you can perform non-linear operations in the data in such a way that you can perform linear classification on non-linear transformations to achieve arbitrary separation. What is the catch here? The success of this algorithm to classify highly depends on the kernel that is used. And this kernel is usually fixed, which means either you know what kind of kernel you want to use to classify some data, or you will never find a solution simply because the machine is not capable of doing that. It means the machine is not expressive enough to solve a particular problem. On the other side, side of the game, we have this thing called the neural networks that are basically gigantic machines or gigantic programs made of a lot of layers and a lot of internal calculations that are capable to learn from data because they are equipped with a lot of trainable parameters. And what I mean by a lot is really, really, really a lot. All these artificial intelligence models that are nowadays changing the world, I can think of ChatGPT or all the generative models for images or standard classification tools and so on, are equipped with millions or billions, English billions, of parameters. The challenge here is to train those parameters, and this is possible thanks to something called the backpropagation, that in my opinion is the key advance that allowed artificial intelligence to flourish in this recent world. If the neural network is large enough, it can represent any mapping from any kind of linear mapping. So what it means is, if I have a big enough machine and I have a big enough training method, I can make this machine learn whatever you want. So you don't need to know anything. You don't need to think about where the holes of the bullets are on the planes. You just feed this data into a machine and the machine will find a way to learn about it. So you don't need to think. This is one of the most important parts of the whole neural network formalism. Now it raises some other problems, like for example, interpretability of the neural networks, saying, well, what are they doing? How can I understand what kind of calculation this neural network is performing on my data? And the answer is, well, you can really not know it because you left all the optimization to the black box. So those are the two extremes in the machinery. But of course, you can always think of some sort of middle term, right? For example, you could have some kernel methods that are determined, or they have a few hyperparameters. Like for example, these two elements that are the Gaussian kernel or the polynomial kernel. Then you can say, well, you have some sort of flexibility in our kernel that you can that you can manipulate, that you can train for better performance. But still, only if the kernel properly captures the structure of the data, classification can be successful. On the other hand, on the neural networks, training is done through gradients, so it's very, very efficient. But since it's purely heuristic, there is no guarantee of the quality of the final trained algorithm, even though it's normally work. And every layer of the deep neural network adds some extra step in abstraction and is translating the data more into the machine language than into the human language. When would you like to use kernels? When you have some structure that you would like to take advantage from. But when to use neural networks? When you have no idea what is going on. Are they both methods? Both methods are different. Well, in principle, nothing prevents me to use a neural network as a kernel. Then you could combine them. But what for? And in principle, nothing prevents me from using a neural network that has some sort of bias into learning what I want the neural network to learn. And this is already some of the philosophy of the kernels behind the design of this neural network. So I would like you to think about these two methods.
Стой, это что за... А вот,
Yeah,
блядь, как мне скопировать ссылку?
okay. If that was the question, I didn't get it. Sorry.
I don't think it was a question, Adrian. Just go on.
Yeah. I was loud comment. Okay, thanks. So I would like you to think of some sort of a spectrum between what we know what to do and we don't know what to do. This becomes very much more important in quantum, and this is where the quantum machine learning algorithm starts. So the same way we have some kernel methods, but in this case, our kernel methods are simply operations that can be performed with a quantum computer. Why with a quantum computer? Because in principle, this quantum computer should be capable of providing me some computational power that is not achievable for a classical computer. So there is a technique, which is you have some quantum kernel, and then you use a standard classical supervector machine for classification. And this is enough to prove quantum advantage. And this has been done in this paper by the IBM team. On the other hand, quantum neural networks, it's a much more general way that should allow you to try to tackle different and try to address different problems, right? And again, you have to perform some sort of training algorithm. But now the question is, well, this training has been shown to have some issues like trainability in the celebrated example of the Barren Plateaus that I'm pretty sure at least some of you have already heard about it, or expressivity or generalization bounds, in particular in the works by Matthias Caro. So the thing is, again, we have something which is very specific that gives you quantum advantages, and you have something which is not that specific that has a lot of issues. This puts us in some map in which you have these two different scenarios, which are inherited from the classical machine learning framework and field that now we have to translate. So on the one hand, we have kernels with provable quantum advantages, which is what we are looking for, but they are super limited in scope. They can only solve a bit very specific type of problems, and they are in general not useful. They usually need fault tolerance. I mean, a computer that is capable of doing any sort of operations. And there is analysis available from learning theory and complexity theory and all of the complicated theories that you can think of. On the other hand, you have these quantum neural networks that are variational, those general, but they perform very poor, or they are classically simulable, and they are very hard to train. There is some analysis available in certain architectures, but definitely the amount of architectures that you can analyze is very small with respect to all the architectures that you could possibly think of. In the middle of that, you have some sort of terra incognita that we don't know how to deal with. And in my opinion, and this is the main message of the talk, we need to understand what is there, and we need to develop tools to navigate in this area where dragons lie, so that we can find some interesting problems and quantum advantages that are useful for a general purpose, that are not so narrow that only theoreticians, hardcore theoreticians care about, and that still can give you some sort of performance. This talk, the framework that I would like to present you for analyzing is about that. It's about tools that allow us to navigate the sea of lack of knowledge that we have right now. My proposal, or our proposal, is a numerical analysis, several tools to analyze variational QML. So we need some systematic tools that allow to analyze heuristic approach, because neural networks depends on heuristic, and we should go in the same direction unless someone has a really brilliant idea that I haven't seen. So we would like to explore in the frontier between kernel and quantum neural networks. These tools are not aiming to substitute any sort of theoretical research. This is super important, but we would like to equip the researchers worldwide from different backgrounds with useful recipes and useful numerics that can give you some information about what are the features of the performance, what are the features of the algorithm that you're playing with. The extracted insights are hopefully educating the future design of QML methods. And after that, I can start with the 3 different approaches that stem from the same central pillar, which is my general recipe here. Consider a parameter and data-dependent quantum circuit that depends on theta and x, being the ansatz for a learning problem. I don't want to restrict myself to any sort of U, to any sort of data, to any sort of parameters. We just say that the parameters theta are controlled by classical computers and the x are given from some data. That's it. So to analyze these ansatz, our proposal is A, choose several instances of theta and probably maybe some instances of x as well. For each of those, measure some observable that is used to perform the learning algorithm. Usually this is the cost function, but it could be some other things. So the data for each of the thetas is now stored independently, and all data are processed in a classical computer. Then we can extract the specific properties of the ansatz. I would like you to think about this step between 3 and 4, which is the data is stored independently and data is later processed in a classical computer. Therefore, there is no quantum classical communication overhead. And this is a massive problem that the literature for quantum optimization has been addressing because of the Holevo bound. At any point that you measure something or you measure a quantum state, you are losing a lot of information, lots of information that you would have to repeat the measurement several times in order to get just a glimpse of what is going on. Here we don't have the problem. So it's some efficient use of available resource, and so that we can educate or guess more or less informally what we should be spending our resources on. The method does not rely on any analytical assumption. It is usable for any ansatz, and we can use these methods to check if something is useful or to guide the search for an appropriate ansatz for a given problem. And now all of the game is about, well, what are the relevant properties to be examined? I'm giving some examples here, but I would like to invite you, anyone that is interested, or anyone in the community, to give more properties and provide more examples that can be useful. Let me add also here that inspiration is drawn from the field of classical optimization. There is something called the exploratory landscape analysis that has been used for people from the classical optimization field to optimize really, really, really hard functions to optimize. If they were capable of extracting things for the most complicated function that you can imagine, we can also do this kind of stuff with a quantum machine learning perspective. So I'm gonna get technical here. First work that I'm presenting is vanishing gradient or background plateaus. So this has been a topic that has been addressed in the literature very extensively. In my opinion, it's a bit too extensive for the depth of the concept, but anyway, it has attracted a lot of attention. So what are background plateaus? Background plateaus are basically saying that the variance of the gradients of a loss function decay exponentially with the number of qubits of a quantum computer. What does it mean? It means that there is a huge concentration in the landscape of any function that you would like to train. Hence, look at figure A. If you are somewhere in the flat space at the top of the figure, you don't know where you are. Everything is so flat that there is no direction, there is no downhill to go to. On the other hand, if you have something like figure B, then there is always some direction to follow, and in order to reach some local minimum. What are some theoretical sources for the background plateaus? Are two designs, if anyone is familiar with it, entanglement, layer ansatzes for different kind of observable deep circuits, controllable circuits. Basically, anything that tells me that I'm exploring the space more or less uniformly is leading me to background plateaus. And this is quite bad. So, but what if we escape from the aforementioned assumptions? And there are already a bunch of works that I haven't cited because I don't have any space in the slides, but are very interesting, that come, for example, in the concept of warm starts, that is being more or less close to the minimum, or biased parameter distribution. What happens if you explore in a very particular way that is helping? Or you have kernels with a bit of variationalness, which is also a variational circuit, but you start from a very specific place, so you are not exploring everything. In those cases, analytical approaches are no longer applicable, and this is where our game comes into importance. We have something called the information content, which is a tool that allows me to numerically analyze the average size of the gradient. Again, based on the exploratory landscape analysis, and we need to sample only linearly many points with m the number of parameters on the ansatz. So what is it in a nutshell? So you have this you have this numerical recipe that tells me, okay, if I can sample from this landscape, you shove all this bunch of data into the information content, and it spits out a number which is the average scale of our derivative. And this is robust. This is very secure. It's very efficient. And it has been, and we have shown theoretically that it gives you some very specific bounds with this property this average scale of the derivatives. So how do you compute it? You sample points and you connect them randomly through random walks. And in this random walk, you can compute the changes that are larger than a threshold epsilon. That means if the random walk goes up or down or stays the same with respect to this epsilon. The information content, or H epsilon, is some partial entropy of steps up, down, and equal, which means that if the partial entropy is high, then the random walk varies a lot. While if the entropy is small, then the random walk does not vary at all, which means it has to be flat. Epsilon is the relevant scale and is going to be a proxy for the average scale of the derivatives. This relevant scale is giving me the maximal variability or maximal flatness of my landscape, and this is the number that I want. Long story short, saying, okay, fine, this is all a theoretical construction, but can we make it useful? And the answer is yes. So we took for the experiments a couple of known problems for background plateaus that tell me if you have this particular ansatz or these two particular kinds of ansatzes, you should not see background plateaus or you should see background plateaus. And by making these computations with the information content very efficiently, we match the theoretical results, right? So you can see here all our results. And the important part here is in the orange lines in the right figure, you see how you have a straight line, which is exactly the theoretical prediction. While in the blue line is in the background plateau free regime, and we see how it saturates to a certain point and doesn't go beyond that. Fine, this is for the left figure. For the right figure, it has to do with the number of layers, and the variability is a little bit less clear because background plateaus are a scaling statement of n qubits. Another thing that we have is numerical scaling factors, which is fine. You can have exponential decay, but it's not the same to decay as e to the n or e to the minus n that to decay to 0.00001 to the minus n. The consequences are fairly different. With this methodology, we can have some numerical estimations of what is the scaling of our approach, which means that we can be much more precise than the theoretical analysis. And why is this? Well, simply because we don't approximate, we don't make assumption, we don't say, well, we don't really know how to compute that, but approximately or up and bounded by that, we just have some numbers and spit out again relevant number plus what is the relevant number plus the error that we have, and that's it. And you don't even have to think about it. So how to use that? Saying, well, if I have my own answer that I don't know how it works, yes, sample data, shove into the information content, and you will get a number out, and this number will let you know if you have enough budget to perform any optimization or not. So second question or second section or second word, this is about the expressivity. Usually we have this concept in the notion of variational quantum algorithms, which is about expressivity, right? And in certain contexts, this is related to closeness to T designs. T designs are a rather technical element that are devoted to how uniformly you cover some space. If you have a T design of a probability distribution, that it means that you can match up to the Tth statistical moment. There is an example that connects, for example, expressivity and trainability, which is if an answer is expressive, that means it is a 2 design, then there are background plateaus, then it's a big problem. However, these T designs have much more stronger implications. So it's a really uniform description of the answer or the landscape that you are playing with. While we usually focus on something not that strong, something that we have tapped the all shadowed or observable shadowed T designs. Say, definition. An all shadowed T design is a set of pure states that looks like a T design when measured with respect to one observable. That is the game. And this is still enough for background plateaus. If the answer is an all shadowed T design, then there are background plateaus for this particular observable, but we don't know about anything else. What we are giving here is some proposal to have these random states and analyze them through the expectation values of the given observables by connecting to something called the Dirichlet distribution. Again, for the more formal attendees in this talk, this is somewhat similar to a Weingarten calculus. We can chat about that. Our proposal is you have a set of states S, and we would like to verify if it forms an O shadow T design by selecting the spectrum of the observable and comparing the strict numbers using some Monte Carlo sampling to analytical results. The number of samples that we need scales at that last stat, which is quite nice in some sense. It goes as T squared, it goes as epsilon squared, so not that bad, close to standard Monte Carlo explanations. And you have this trace to the power of T, but it's trace over N. So the moment our trace is more or less small, then the additive error that you have for estimating this is quite small. Of course, this is not enough to signal T designs. This is only enough to signal all shadowed T designs, which is similar as saying, well, you have an entire sphere, and this would be a T design, but if you project it into a plane and you have only a disk, this is just an O shadowed T design, but you don't know anything else about the rest of the sphere. What is the perspective of that? Well, we can verify this O shadowed T design with increasing effort on T. And this method signals when a set of states is not an O shadow T design. But if it is, then you don't know about the rest of the elements. So let's say, for example, the set of states given by Clifford circuits. This we know by definition that it's a tree design. And then for every observable, our recipe will signal significant difference in being a T design only for T larger than 4. So you can check if it's a 1 design, 2 design, 3 design, and a lot of them you will have the check. And for the 4, it will fail, meaning this is not the T design anymore. An application that you can think of for variational is you can sample states drawn from a quantum circuit, and following our recipe, we can signal if those states form a 2 design with respect to some observable. And this would be a complementary numerical approach to the information content. Now, how can we step up from O-shadow t-design to actual t-designs? And there are two tricks that we are presenting in the paper, which come as follows. First of all, we need permutations. The spectrum of the observable is, when it's degenerate in particular, tells me that our method cannot distinguish between the elements in the same eigenspace. Which means if you have some eigenvalue with degeneracy half of the Hilbert space, you could have all of the samples, all of the states going into exactly the same state, in eigenstate, and my method will never see it. However, if I apply some permutation before the observable, some random permutation, then you can verify that S follows the same Dirichlet distribution in the basis of the observable or in a permuted basis. By applying a statistical average over many of these permutations, you randomly change the order of these eigenstates, and in the end, you can get something like you have some actual number or not. Like you get some states that are t-design or not. After this, the next step that you need is to use the mutually unbiased basis, which are two mutually unbiased bases are bases that can be written only as a superposition of all elements of the other bases. So the choice of the observable diagonalizes the Hilbert space, but is still insensitive to certain aspects of the randomness, for example, the complex bases. But since the mutually unbiased bases are informationally complete, we can average over all these MUBs, and this can be done efficiently, and statistically verify t-designs. So statistically averaging over the permutations and the mutually unbiased basis will tell me that S is statistically close to a t-design and no longer an O-shadowed t-design. So it's a cheap way to say some things about the ansatz. Finally, the third section and third work that we presented is the classification power that has to do also with the randomness. So consider this classification algorithm. Data is given in a form of states, and the class is given by this mathematical operation. So assigned with respect to a classification threshold. Literature tells me, oh, but if I want to be a quantum machine learning algorithm, then I would like my answer to be as expressive as possible so that it can solve everything at the same time. What I'm telling you here is exactly the opposite. We need the elements of the two classes to be classified to be as distinguishable as possible. So contrary to expressive ansatz. As a illustration. So say that you have label blue or 0 and label red or 1. Everything which is in the middle is potentially misclassified, in particular because you have some measurement error because of the quantum nature of the work. For classification, our data-induced states should be as concentrated as possible to the sites, to set to the value of the observable 0 and 1, or set, which is just flipped, 0, as concentrated as possible. And this makes classification hard because it's in the opposite direction to the standard way that we have seen. Quantum states tend to be as uniform as possible, and we would like them to go in the other direction. This is why it is so difficult. We can give two results. That one has to do with the information of mean and the variance, that we can bound probability of failure using analogous to Chebyshev's inequality. If you have information to all statistical moments, that we have some bound probability of failure using something analogous to the Heuristic inequality. Right result is stronger than the left result, but it requires more power, but it doesn't really matter for this talk. What I want to say is that we really need to separate how data is if we want to classify. And this is something that we can see again in the DLP, discrete logarithm problem that I have already hinted before for quantum advantage. In our formalism, we can see that the failure probability scales polynomially in n, which is good also with polynomial effort, agreeing with the original references, because this is a very particular kernel that performs this classification or this separation very efficiently. We can also consider, well, what is the role of the observable? The same thing that I was saying before with the 2D signs or all-shadow T designs. If we have this particular state, that is some superposition of elements with increasing number of ones, but only one of them, and C being some classification task, there will be some observable that classifies this perfectly, and some others that classify this randomly. And this is visible in the numerical analysis that we propose. But not only from analytical results, this is you can perform these operations. We would like to use this analysis tool to investigate variational algorithms, for example, using classification tasks of synthetic data. And we have used this reference from Wojtek-Havlicek in an IBM paper, where we have compared a fixed feature map that scales in the number of qubits and re-uploading like kernels and we have used this data-induced randomness to investigate the proposed algorithm, which is basically the following. So for the fixed data, for the fixed embedding, you have something as in the top of the right figure saying you don't know what these blue and red blobs are, but you would like to classify them using some data, which would be somewhat less comparable to the figure A in the side A and the figure at the bottom. While with the re-uploading thing, we will be doing something more in the B side, just moving the data points to wherever I want. Thanks to Berta, I think she's there and she made this beautiful figure. So the thing is, how can we run experiments? Well, we can have these two experiments and compare them and saying, well, as you have some increasing number of qubits and increasing number of layers, you can see that the fixed encoding is basically random because the difference to random is very, very small. And the variance is very large, which means I have no idea what I'm classifying. However, in the re-uploading scheme, I'm still in the right part, saying I can more or less classify. Still, the power of randomness in quantum algorithms is very strong. This is why, as we increase the number of qubits, everything gets closer and closer to random. But something that I find very curious is the fact that if you take some random parameters and just check that, everything is going to be random. So in light of these results, quantum machine learning is an eternal fight against randomness, and randomness is a very powerful enemy. So we really need to think how to overcome that. In the contrary to many other literatures that take random states for using other stuff. So after these talks, these works, I would like to conclude saying we have some current methods in QML that are either not performing or not applicable. You have kernel methods in one side, variational methods in one side. And in the quest for this applicable sweet spot, we propose a series of numerical tools, which are harvesting data from a quantum computer and classical post-processing this data, allocating some quantum budget for data retrieval and requiring no quantum classical communication overhead, which is, again, strong issue here. I propose several examples here, like the average magnitude of gradients, randomness in connection to designs, or data-induced randomness in connection to classification performance. But there are other proposals that remain unexplored. Like, for example, what is the volume of space that my ansatz can cover? How many states I can approximate? What is the number and quality of the local minima? This is a strong problem also in neural networks. Or are there any biases in the exploration of the unitary space? Probably yes, but how do you quantify it? If you have any other ideas, please let me know. Or you have any sort of problem that you would like to address. I'm very interested in that. Future work will hopefully further incorporate more aspects to this research, and I would like to make some community effort that will guide us towards something useful in the field. With that, I finished. I would like to say that this work is mainly based on these three references with Xavi, with Hao, and with Berta, and all of the others. I can give you the slides for all the rest of the reference. Thank you very much for listening. I hope you learned and I hope you enjoyed it. And I'm open to take any question that you can have. Thanks.
Okay, if anyone has any question, please go ahead now. There are like 10 minutes for questions, a little bit less. Okay, in the meantime, Adrián, I would like to ask you just a little thing, like a subtlety. When you were introducing the old shadow thing,
Yes.
with the Monte Carlo sampling bound, I was curious. I don't know if I understood it properly. So the bound is observable dependent, no? Like there's no way you can get an upper bound if you are like observable blind, I guess, or is there any
No.
way to generalize it?
The way to here you mean, right?
Yes, yes.
So the way to generalize it is through the permutation and mutually unbiased basis.
Okay, and that
The-
allows you to get it for any observable.
Yes. No. So the thing is, you choose one observable, and with
Mhm.
this observable is your lens, and with this observable you can extract some information from the set of states. Of course, this lens is going to be only looking into one particular direction,
Okay, yeah.
right?
Mhm.
It's going to look into one particular direction, but there will be some parts of the distribution of the set of states that are not visible because the observable does not allow you to do that. To say this sort of 3D scan, you need the extra permutations and extra mutually unbiased basis,
Okay.
which means, answer to your question, by allowing these extra steps, you don't depend on the observable anymore. But to begin with, the observable is the lens.
Okay, and so the comparison with Monte Carlo sampling would go as the amount of permutations or the amount of elements in the mutually unbiased basis.
Yes.
Okay.
Yes. In this, so this, yes. Again, it's a multiplicative factor.
Okay. Okay, so that's all for my part. If no one else, oh, there's a question in the chat, Adrián.
There is a paper from last year on classical shadows implemented on a neural network via the infidelity as the loss function. It seems scalable and even robust against noise, but they only use it for quantum state tomography to reconstruct state and determine a couple of properties. Well, who I cannot. I don't know which paper is this right now. But yes, in principle, for those of you, if you don't know classical shadows are a way to measure elements so say you have a quantum state and then you perform random measurements on these quantum states, and these random measurements are rearranged in a particular way to extract a lot of properties. This is where the power of the classical shadows come from. Really, a lot of properties. In principle, well, classical shadows is, as it's said in the chat, used for quantum state tomography, and you could use it for that. Could you use it also for this? Probably yes, but I don't know how right now, because you would like to understand what are the statistical properties of an ensemble of states. So what I could think is, instead of just taking the average or statistical properties of the states or pure states, make it into a mixed state or make it into several copies of the mixed states, and on that you can perform classical shadows probably. But anyway, classical shadows is something that can be incorporated to all this framework. It's not in different directions at all. It's quite aligned into the same philosophy.
They're sending the link to the archive.
Neural shadow quantum state tomography. Okay, I'll read it, Jose.
Okay, so if no one else wants to ask, we just thank Adrián on behalf of everyone. Thank you for a very nice talk, and yeah, see you soon.
Yeah, you're on. Thanks, Bea, for the organization.